We'll be talking about standard enthalpy of formation given the symbol delta H naught sub F. We pronounce that degree sign as naught. So delta H naught sub F, that just stands for standard enthalpy of formation. It's also known as heat of formation, as we often refer to enthalpy as heat. Delta H of F, or standard enthalpy of formation, is defined as the change in enthalpy associated with making 1 mole of a substance. Making 1 mole of a substance from its elements in their most stable states under standard conditions. So that heat of formation really means you're forming 1 mole of a compound. And that compound is made up of its elements. Some examples here, you have the formation of carbon dioxide gas from its elements carbon solid, oxygen gas. That reaction has a delta H value of negative 393.5 kilojoules. And since this is the formation of carbon dioxide from its elements, this is referred to as its heat of formation. Likewise, you can see here we have the formation of NO2 gas from its elements nitrogen gas and oxygen gas. This is given a heat of formation value of positive 33.2 kilojoules. And so a word about stable states and standard conditions of these elements. The first thing that you're going to see in our delta H values for heat of formations is that degree sign. We pronounce that naught. And it denotes standard conditions, which means 25 degrees Celsius, 1 atmosphere pressure if we're dealing with gases, and 1 molar aqueous solution. And what do we mean by most stable states? We mean the most common pure elemental forms of our elements. So oxygen is going to be diatomic, nitrogen likewise is diatomic, carbon is in the form of a solid in its most stable state. So to think about this for a pure element, okay, so in its standard state, elements are going to have heat of formation values of 0 when they're present in their most stable state and its standard conditions. So here's an example of oxygen. So here's 3 different elemental oxygens, but the one that's most stable is diatomic oxygen, O2 gas, and it has a heat of formation value of 0. These other forms of oxygen are less stable, and therefore they do not have heat of formation values of 0. Only oxygen gas, the diatomic form, has a heat of formation value of 0 because that's the most stable form of oxygen. So how do we use these heat of formation values to estimate and calculate the heat of a reaction? We have one equation and we call it the Big Mama equation. I've stolen this from a program called NIMSY who referred to this equation as Big Mama, and I've been using it. So kudos to NIMSY for coming up with this. The delta H of a reaction can be calculated by doing the sum of the heat of formation values of the products, subtracting the sum of the heat of formation values of the reactants. So we're going to need to know what the heat of formation values of common substances are. So I provided a link here to your textbook, which has a thermodynamics appendix. So you can either scan the QR code here or the one on your paper, or if you're looking at the digital copy, you can click on the link. So let's go ahead and tackle some examples. We're going to use the Big Mama equation to calculate the delta H, or change in enthalpy of a reaction, or sometimes referred to as the heat of reaction. And we're going to look up the heat of formation values for all the reactants and products using the thermo appendix in your textbook. So you can scan this QR code here on the screen or refer to the one that is on your paper to bring up this thermo appendix with the heat of formation values. So the first thing that you should notice here is that the appendix is sorted by element, the first element in the compound. And the column that we're concerned about with today is this delta H of F, or the heat of formation values, or these are also referred to as the standard enthalpy of formation. So looking at question number 1, we're going to look for NH3. So it starts with nitrogen, so I want to go to the nitrogen section of the appendix. So the best thing to do is use your Control F to bring up your find box, your search box, and just start typing nitrogen, and you'll quickly get down to the nitrogen section. So the main thing that you want to look for or pay very close attention to is the state of matter. So in our problem, it is gaseous NH3. So just make sure that you are using the gaseous NH3 value. It's right here. It is negative 45.9. So I'm going to go ahead and record that value. So negative 45.9, and what I'm doing here is recording the heat of formation values for every single substance. Our next reactant is oxygen, so I'm going to go back to our appendix. I'm going to type in oxygen into my Control Find or Control F, oxygen, and real quickly, here we go. And so our heat of formation value for elemental oxygen is 0. All right, 0 here for oxygen. And I'm going to repeat this process for the NO and the H2O. So back to our nitrogen section. Search for nitrogen one more time. Oopsies, nitrogen. There we go. So we're looking for gaseous NO. 90.25 is its value. And then finally, H2O liquid starts with hydrogen, so I want to type in hydrogen into my search bar. And hydrogen. There we go. We're looking for H2O liquid. Again, pay close attention to the states of matter. You want the liquid water. So it's negative 285.83. Let me just make sure I recorded that one correctly. Okay, we're good. All of these heat of formation values are in kilojoules per mole of the substance. And we're going to follow our Big Mama equation here. We're going to take the sum of all of our products, remembering to multiply their heat of formation values by their respective coefficients. So here are your products in red, and we're going to do the same thing here for our reactants. We're going to multiply their values by their coefficients, so 4 and 5 for that 0. So our delta H is going to be equal to 4 times 90.25 plus 6 times negative 285.83. Okay, so this is my product, the sum of all my products, and then I'm going to subtract out all of our reactants. And you really don't need to do the 0 part, but I'm just doing it now for emphasis so you know where I'm getting these numbers from. So we go ahead and calculate this. Alright, so what I've done here is I have multiplied all of the heat of formation values by the respective coefficients, and I have a sum here in red of my products, and now I'm going to subtract the sum of my reactants. And the biggest mistake that I see students make is not paying attention to the negative signs. So just respect the math, make sure you are following your order of operations correctly, and you should arrive at the correct answer of negative 1170.38 kilojoules per mole. So with that negative sign there, we know that this reaction is exothermic. One word about units. Remember that delta H for a given reaction should have a unit of kilojoules per mole of reaction, RXN there. All right, onward to number 2. All right. Problem number 2 here, we're going to do the same thing. We're going to look up the heat of formation values for all of these substances, and then we're going to do the sum of our products minus the sum of our reactants. So back to our heat of formation values in the appendix. Again, scan that QR code if you need it. We're going to look up aluminum in our control F. Look up aluminum. And you'll see here that aluminum solid in its elemental form has a heat of formation value of 0. And a word about this. As we've stated before, all elements in their pure, most common form at standard conditions, they're all going to have a heat of formation value of 0. So aluminum solid, standard conditions, delta H of F of 0. So automatically I can just write a 0. I don't really need to look up that value because I know that it's in its most common standard elemental form. I am going to need to look up this iron oxide. So back to the appendix, we're looking for Fe2O3 solid. So we're going to type in iron into our find box. And we're looking for Fe2O3. Be very careful. Make sure you pick the right one. We want this one here, negative 824.2. Negative 824.2. And I'm just going to go through and look up the other values. Aluminum and iron. Well, I'm going to do iron first, just because we're on the iron section. And you'll notice here, Fe solid. Heat of formation value of 0, because again, that's iron in its elemental form. At standard conditions, it is going to have a heat of formation value of 0. All right, back to aluminum, where you need to look up aluminum oxide solid. So type in aluminum into my control F. Aluminum oxide, negative 1676. All right, so negative 1676. And we're going to multiply by their respective coefficients. So aluminum gets multiplied by 2, iron oxide by 1, aluminum oxide by 1, and iron here by 2. And then you do products minus reactants. All right, so my products are in these red brackets, so it's just negative 1676 minus the sum of my reactants, just in these black brackets here, and then we just finish up the calculation. I get a value of negative 851.8 kilojoules per mole of reaction. So again, this one is exothermic. Be mindful, watch out for those negative signs. That's the biggest mistake I see students make. And then also your units, the units matter, kilojoules per mole of reaction. Moving on to number 3. All right, they want us to calculate delta H again, so why don't you hit pause, you try, come back and check your answer in a minute or so. Okay, so you should have tried this problem on your own. Now let's check for your understanding. First thing to do is look up the heat of formation values of all of these substances. Alrighty, so here are my heat of formation values for these substances. Next step is to multiply them by their respective coefficients. So you're going to want to multiply your products by their coefficients. And then we do our same thing for our reactants. And the next thing is to do the sum of the products minus the sum of reactants. All right, plugging and chugging into our big mama equation, products minus reactants. We calculate this and we get an answer of negative 1451.94 kilojoules per mole of reaction. One thing to note, and I'm emphasizing here again, that elemental oxygen at its standard conditions, which means 1 atm and 25 degrees Celsius, it is going to have a heat of formation value of 0. I don't even bother to put it here in my calculation. So sometimes, word of advice, sometimes you're not going to be given the heat of formation value of some elements because we have to know that they're going to be 0. So we just assume they're 0. Don't think that the problem is like not giving you all the information that you need to solve the problem. So there you have it, the Big Mama equation. Sum of the heat of formation of your products minus the sum of the heat of formation of your reactants.